Hello everyone. In this video tutorial I'm going to show you how to conduct or perform a 4-point bending test in ABAQUS software. So we have a very simple beam which has 2 meter length and 200 by 300 millimeter cross section, 4 rebar, 4 number of 16 rebar, and also a straps number which is 6 millimeter diameter, and with totally 70 millimeter. And we will see we want to distribute this 70 across this beam, and the location of loading is from end of the beam to the first point 600, and from here to here 100. We go to ABAQUS and quickly first create a concrete beam, and I can call it concrete beam. It's a solid 3D. I give 200 deformable, and I can write here. The first point is here, which is minus 100 in x direction, and in y direction is minus 150, and second is positive 100 and 150. So this is the beam cross section, and the length is equal to the extrusion depth, 2000 millimeter. The second part is we want to create straps. The straps is we want to use wire, and we want to give a cover, a clear cover between these two. This is 20 millimeter. So both side is reduced 40 millimeter, which is 160. So now it will go to minus 18, and from top 130, minus 130. Here, and the second is going to be 18, 130. This is the straps, and the last one is we want to call rebars or longitudinal rebars. The longitudinal rebar is from this point to the 2 meter. So we want to give a 20 millimeter both side cover. Even we can ignore that one, it's okay. Let's suppose it's the same with length of the concrete. Now this part is finished, and we want to go to one more thing for the loading area. We can use solid elements. Also we can use analytical rigid, discrete rigid. This is quite good as a shell element. It can apply the load as well as, but in practical mostly we have some sort of steel material with very deep length or thickness. Then we are applying the load in that area, even using some sort of wood. So I use a solid element using part 4, and I call it loader or support. That support is 10 by 10, 100 or 10 by 15, and the extrusion is equal to the depth of equal to the weight of the beam. So this is 100 millimeter. Now we can go to the next material properties, and we want to create material. Here is some material available, and I can add this Chinese code structural steel, and this is Q3, and the density is here. The plastic is this one, and the elastic, and this the plastic is this one. Even I can use that just elastic in the first yield point, but it's better to see how these behave when it has a very large plastic and plastic strain and also stress. The second, we have concrete. It is a concrete, and I used CDP 25. This is a CDP 25 material. You can get this data from, there is some web tool, you can create it, or if you don't know, please put in the comment, I will give you this material, or you can download from my GitHub. This is a compressive, and this is and also some other the plus C properties. And the last one I want to create is a elastic. Just elastic is just and I want to conduct this test using dynamic test, because the dynamic is quite fast, and for large nonlinear behavior that can converge easily. I give 7.85 E minus 9 ton per cubic millimeter, and the elastic is 200,000 megapascal and 0.3. So that we don't consider the behavior of this loader support, so just we want the property should be elastic. Now we created the first concrete, solid concrete, and the second is also, we have another solid called support, and this time use elastic. And another one, we should create some profile. One is a circle, which we're gonna using called rebody 16, so using the diameter is 8 millimeter. And then another one is for stirrups. Stirrups is using 3 millimeter. Now we want to create one section for called rebar. That's beam, and using beam element, and here is the rebar 16. The material is going to this material, and another one is going to stirrups, and this time we're gonna give the stirrups on the same material. The material is finished, and one thing I should say that we need to define orientation, because this is a beam element. Beam element always needs orientation, so I can give this one is okay, and this is a circle, so it doesn't matter which direction you want to give, and the x, y, or large I x or a large I y, and the same for this one, assign it. But for other sort of cross section, you should properly define that. Material is still concrete. Concrete is left. Support first, assign support, and this is called support, and this is the concrete beam. Now the property is finished, the assembly them, and I want to bring the concrete. Okay, and I want to bring the stirrups. Okay, now we can here we can go to the color geometry. Okay, we can use this transparent, and it's in the exact area. And what we want to do is just we want to first select that straps and bring it a little in the z direction. We want to take 0 0, and that's also 0 0 in the y, and we want to bring it 20 in the z direction. Now we want to second populate that one. I can go to here, parts, and complete should be removed for a while. Now next is we want to populate this. Populate it and back here and adding everything. Now I should give the direction, and this is the direction, and we want to remove just one. Let's see how many we can reach. This is 16. Now I want to give 140. The distribution is uniformly. We didn't consider this area should be large more and this area should less. So for your experiment, then you should check properly. And this okay, 16 rebar. And the next is I want to bring the rebar. And now I want to rotate this. I want to rotate based on this y direction, and it's like this. I'm going to select it and taking this point and putting to this point. Now I want to do one more. I can go back here, and then I can take this and going to push it minus z direction. I'm going to 0. I'm going to 0, and this also x y is 0 and needs to be minus 20. Now it is correct. So there is no so all things inside the column. And now next I want to take that rebar and just asking this direction. This is 160, and this is in the top direction is 260. We have 4, and it's okay. And now this is completed, and we can go to bring everything same. So what I want to do is I want to take all them and just go to take this line and change. Sorry, I should rotate this. And I'm going to rotate to put x in xy instead of that. And one more thing is I'm going to select this one. I want to take this point, select it this point to 0 0. Sorry, this one. Selecting this one. And now, sorry, it's wrong. So we did a little mistake, and I can fix them. Just go to this one and select all this this point. Okay, I can select one more times this area and going to this area, and this time 0 and bring into -20 little to the x direction. Now this is fixed, and the last thing, I want to bring the support and creating the support location. But before this, I want to go back to the part and create some partition that specifically want to apply the support in that area. Here is the create data plane, and we can go to one data plane should be exactly in this area, 100, and then one should be here, which is 50, less than 50, 7575, and I can go to here. It's called yes, create offset, this one, and going to enter and flip that side to be 100. 100. This is one, and again I'm going to this time from here to here should be okay, and 575, and then again okay, and 575 plus 100. And now we have here, and then okay, and then this time again we go to we have these two, and the 3 is here. Now we have, if I go to dimension, and I can take this point to this point, sorry, I can go to here, 1325, 1325, and again okay, 1325 plus 100. Now we have this 3 point, and we can go to again, this time this should be flip, and so exactly this 19. So this is finished, and we want to do partition as well. Here we can use this, yeah, partition data plan. You can select this one, select data plan here, and select here. This partition don't has any impact to the analysis or result. Just this is for create a nice mesh. So we have created, and we can go to assembly and bring the solid, and now we want to bring the support. I'm gonna offset to go somewhere else, and we want to take this point, and I can put this here, exactly here, and then I want to create more of this one. To be 3 more. I can select this one to here, and one to here, and this one here. Now it's finished. We go back to the step, and we want to create a dynamic test. The dynamic is for for such kind of especially for concrete, and when using CDP or nonlinear materials, so it's quite good, faster, and you can go to use explicit. I want to use a list. The dynamic should use looks like or semi-static by giving a large amounts of time or period of time, at least conduct 5 seconds. So in case also you can use masking, but I want to ignore this. In here in the output data, you can go to the failure, stress strain, and also this is a failure. You can consider the damage compressive behavior as well. And so the interval also we can check it. The next thing is this is the output. This output is no need, but instead of this we want to create, we're going to back, no, we're going to go to back here. We want to create some output. So we want to apply this force, these two force here, and we want to get the displacement in the middle of this point. So we have 1 point here, 1 point here. In the same time, we want to apply displacement instead of load. In same points will create as will give us forces, force and displacement. So then the average of that, the average of the force and the displacement will take the maximum displacement, and also the sum of that force equal the capacity of this beam. So I'm going to create some. Before that, I'm going to create some point which I want to apply. So I do this method, and you also can use another method to get these results, and then you compare is it correct or not. So I'm going to add some reference point. One reference point is here, one reference point is here. So I will measure these 2 points, and then the average of these 2 points is the middle point. So that sum of these two force is equal the force which is adding in the created by reaction in these two end of the beam. Now in the here, and I go to create first a set, create a set, and in the set, and I can call it displacement set. So the displacement set 1, I should go to create one more. I can call this 2, these 2. Now I can go to back here. Here is using set, and first one, here's one thing. If I use every x unit of time, let's suppose I want instead of that point that I want to use time, at least 0.01 second, which creating, if I divided 5 by this one, it's about 5,000 or 500 point. Here I want displacement in the y direction, and also reaction force in y direction this point. Again, I want to create the same u2, going to using set, and this time is 2, and using x increment of time of 0, 1, and again u2 in this point. and using here reaction force 2. This is okay. We created two outputs. Now we go to the loading. In the loading, we want to apply a load displacement here. First, I want to create a boundary condition. Sorry, before the load, I should go to the interaction. I should create some interaction. In interaction, first I want to create an embedded region. Embedded region, which is the contact between rebar and steel and concrete. This is concrete. I'm going to remove it, and here is suppose I want to remove it. Concrete also remove, and now just we have rebar. So I can go to here, select all rebar. Now it's called wall model. I'm going to select just adding all. I want to get the concrete. I can select concrete and replace. Now I can select concrete. So this is the embedded region which is created between concrete and also rebars. So the next thing is I want to create some contact between these supports and concrete beam. Here is called find contact. There is 4 contacts. I want to use them tie. There is tie together. Okay. Now one more thing. I want to create some coupling. We want to couple this point across this here using coupling. The point, coupling this point. Coupling and selecting this. It's okay, and one more coupling is needed to this point. We finished here. When we go to the loading, now first we want to in case you also can create a simple supported beam and see the result, but I want to do it fixed support, this area and this area. Now I can go to intercase. Now next is here is called displacement in a dynamic. Using this one, I can go to set and I can select this one. Other direction is 0, but in direction 2 I want minus 100 millimeter. It requires some amplitude. So I want in 0.0 and 1 should be 1. We have 5 seconds. I should create at least go to after this is 2, 3, 4 and 5. Now in the 0.2, 0.4, 0.6, 0.8 and finally 1. So in a 5 second that 100 should be applied. Okay, and we can go to apply here. Now again this is a created, and I'm going to copy this called displacement T2. Go to edit and the point is these two here. So the same procedure for both sides. Now we go to mesh and create mesh. This is mesh, and I can give a mesh at least 50. We're gonna go to here in the element element. I'm using explicit rebar, and select rebar, and this will be 100. At least 50. The same we should apply explicit, and here is explicit. We have straps 50. Yes, and we're gonna go to here, apply explicit. And the last one is support. That 20 is enough, and we're gonna go to yes, explicit. Everything is finished. Now we can see this is in case if you want to do a mesh sensitivity analysis, then you can change the mesh and perform a mesh. Now we go to here and we conduct create a point test. We can submit it. The following parts have some element without any section assigned. Straps, rebar. Straps, rebar. Go to the parts, the section is not assigned. Straps, assign. With E forward assign. This is assign, and here is the rebar. Go to assign, and this is rebar 10. And if I go to here in the view display option, going to rendering, yes, it's okay. Because we already giving the orientation. Now we're gonna submit it. And we're gonna check. In the monitor, if we found some error, we're gonna fix. Otherwise, it will. And now it's called started, and then it's submitted, starting, and we're gonna complete it. And yeah, it's completed, so there is no error, and wait some moment to start. So the first step is starting, and this is a 0.1 second, so we have 5 seconds. So until the 5 second we should wait. After finish, we will check the result. The total time period has reached 1.1 second, so I think it's about 25 or 23 millimeter. The concrete don't have too much tension resistance, so when we push this 25 millimeter exactly, they will be crack and also failure. So we want to stop this here, and I want to stop. I'm going to go to the result. So this is enough. One thing which is quite important for explicit analysis is it can, after a very large failure, it can also continue to finish until the end point. So, but we don't need to proceed until the end. Now here's the one message trace of the rebar. So it's not reached the yield point. Yeah, it reached the yield point because the yield is 235, and we can go to see all, and then we're gonna back to here. We're gonna just see the concrete. This is the concrete. is about 9 megapascal, the total strength, and we're gonna see the damage. So totally damage this area, and except this area is left. We'll go to back to see how this damage is starting. So this damage is starting from this point and this area too, because significant movement is here, so it will start to in this reason we have to provide more reinforcement here, and then it go to propagate across the entire beam. Now next we want to go to create that output. We created the output. The first is 2 reaction force. We want to save this as a sum of this reaction force. I'm going to call REF and save another. We're going to select these 2 and we're going to save it as an average. We're going to as average U2, and now we can go to here and we have the 2. Remove this and just we want to see plot the so this is the graph. It's a little noise, and I want to take this noise by using a filter, and here you go to here filter, and it's called pattern filter. So I'm going to give this RF and a frequency of at least 0.5. If I go to plot, and what we're gonna see, this is the curve we will get, but this is very thin, and I'm going to give this 2 by 8, and then let's see how it looks like. So this is better than the previous one, so I want to make it a little more smoother, so that will be 7. Okay, now I want to save it again, REF 2, which is the reaction force, and I'm going to create a combine, and the first is average U1, but before, because it's a negative, -1 should times and the U2, and again a -1 should times to the REF2. So now I can call it FD curve, force displacement curve. Now we can go to F force displacement curve, and here is the force displacement curve. Here is, so the structure resists about 105 kilonewton, and then it reduced back. Looks like the concrete compressive behavior. So this is the end of the tutorial. If you have any question, please put in the comment and I will find time to answer you. See you next time.